Now we'll discuss the analysis of acceleration of a particle in two-dimensional motion. We know very well that acceleration is responsible for change in velocity vector. And whenever we talk about velocity vector, it includes magnitude as well as direction. If magnitude of velocity vector is changing, it is because of acceleration. If direction of velocity vector is changing, it is because of acceleration, because acceleration is responsible for change in velocity vector. Let us consider two different cases, one in which magnitude of velocity changes, other in which direction changes. Like for example, say we are having a body of mass m moving with a velocity v vector in this line, say this is the line of motion of particle, and a force is applied onto the body in the direction of velocity. It is obvious that the acceleration of body can be written as F upon m, and in this situation acceleration will increase the velocity because force is acting along the direction of velocity. So we can say in this situation magnitude of v vector increases. Similarly, if the force is applied opposite to it, then we can say magnitude of v vector decreases. But here whatever is changing is the magnitude of velocity vector. If we consider another case in which say body is moving with a velocity v vector in a line of motion, and we apply a force F vector onto it in perpendicular direction. It is obvious if force is applied perpendicularly, the direction of motion of body changes. Again, if we talk about the term acceleration, it can be given as F upon m, which we all know. Here, depending on mass of body, we can say the value of acceleration changes. Here, as force is acting perpendicular to velocity, it is neither acting along the velocity in its direction nor it is in opposite direction. So it is neither supporting nor opposing the velocity vector. So magnitude of velocity will not change, but the direction of velocity changes. When body reaches from this point to this point, you can see the velocity vector direction changes. So this force is responsible for change in direction of velocity. If say mass of body is more, we can say acceleration will be less. If acceleration is less will be the change in direction. Say we consider two cases. One is the case in which body is having mass m1, it moves like this. If body is of mass m2 and say we consider m2 is less than m1. So if body is lightweight, its acceleration is more. So direction change will be more. So body will be moving in this direction, its velocity vector will change relatively more compared to m1 if body is of mass m2. You can see it was earlier moving in this direction. For a heavy body which will have a high inertia will oppose the change in state of motion. So force will be able to change the direction of velocity less. If m2 is less, body is having less inertia or lesser mass implies higher acceleration. Here acceleration is responsible for change in direction of velocity. So change in direction of velocity is more in case of m2 because acceleration of second body is more than that of first body. In this situation we can simply state direction of velocity vector changes. But here magnitude remains constant. Always remember whenever a force which is applied 90 degree or normal to the direction of motion, it can never change the magnitude of velocity. It is only responsible for change in direction of velocity. Let's discuss these two cases one by one in detail. Let us discuss the situation once again. Say we are having a body of mass m. It was initially moving with a velocity v vector along a line. So this is the line of motion of body. Say we apply a force F onto it. This is a F vector force which is acting at an angle theta to the line of motion. Now during motion we can say the force which is applied to it in the direction parallel to velocity, this will be F cos theta, and the component of force which is acting perpendicular to velocity vector, this will be F sin theta. Here we can say F cos theta is in the direction of velocity, so this is responsible for change in magnitude of velocity, and this force which is applied normal to velocity vector, it is responsible for change in direction of velocity. So if we calculate acceleration along velocity vector, this we can write as A parallel. This is acceleration parallel to velocity. This can be written as F cos theta upon m. Because this acceleration which is parallel to velocity vector, it is because of F cos theta. This is the acceleration which is along velocity vector. For this acceleration we can write it is responsible for change in magnitude of velocity. This vector or this acceleration component which is acting along the velocity is responsible for change in magnitude of velocity. Similarly, if we find out acceleration normal to velocity vector, this acceleration is certainly because of F sin theta, it can be written as E perpendicular, and this must be equal to F sin theta upon m. This is the component of acceleration which is acting perpendicular to velocity, and obviously we can say the acceleration which acts in the direction normal to velocity, it is responsible for change in direction of velocity. So these are the two accelerations which always play the role in changing whether magnitude of velocity or changing direction of velocity. And acceleration vector or net acceleration, it can be written as total acceleration. It is the vector sum of parallel component and the normal component of acceleration. Let us discuss the analysis of acceleration in a practical two-dimensional coordinate system. Say these are the coordinate axes xy, and say a particle is moving along a path like this, and at a position particle is at a particular location where it is moving with the velocity v vector. At this position, if say a force F is applied onto it, which is acting at an angle theta from the direction of tangent or the direction of velocity, we can say the force which it is experiencing along the velocity will be F cos theta, and the force which it is experiencing perpendicular to the velocity will be F sin theta. These are the tangential and normal component of the force which is applied onto it. So here we can simply state this F cos theta will provide an acceleration which is responsible for change in magnitude of velocity, and this acceleration we term as tangential acceleration. So here tangential acceleration of particle can be directly written as at is equals to F cos theta by m, which act along the direction of velocity, and it is responsible for change in magnitude of velocity. Similarly, this force which is acting normal to it, it is responsible for change in direction, because at the very next moment particle will reach here and you can see the velocity will slightly change. So this change takes place because of this applied force. If the force would have been acting in this direction, the particle will bend in this direction, not like this. So we can say this is the acceleration, or this is the force which provide an acceleration normal to velocity, which we term as normal acceleration. This normal acceleration of particle which is responsible for change in direction of velocity, and it is given as, in this situation, it is f sine theta by m. So whenever a particle moves in a non-uniform motion in a curved path, it will always have two acceleration. One is tangential acceleration, which is responsible for change in magnitude of velocity, and as particle is moving in a curve, certainly the direction of velocity is changing. That means it must have some normal acceleration which is responsible for change in direction. So we can also talk about total acceleration of particle. Always total acceleration of particle can be given as resultant of the two. In magnitude it can be given as A tangential square plus A normal square, because these two are perpendicular vectors and resultant of two perpendicular vectors can be given by this relation. Now we are going to study in upcoming sections the tangential and normal acceleration of particles.